Imagine staring into the cosmic abyss, not at the vibrant birth of stars, but at their silent, cold demise. Picture a stellar graveyard, where celestial titans, once blazing with the fury of a million suns, have faded into mere embers, white dwarfs. These are the husks, the ancient relics of stars much like our own sun, their nuclear fires extinguished, their cores compressed to unimaginable densities. For decades, our understanding of physics painted a grim, definitive picture for any planets caught in this stellar death spiral. They would either be violently engulfed, vaporized, or flung into the icy depths of interstellar space. There existed around these stellar corpses a forbidden zone, a region so hostile, so utterly destructive, that the very notion of a planet surviving there was pure science fiction. No solid body, no planetary core, no gas giant could possibly endure the cataclysm that birthed the white dwarf, let alone persist in its immediate vicinity. It was a cosmic rule, etched in the very fabric of spacetime, unwavering and absolute. Until, that is, we detected something impossible. To truly appreciate the shock of this discovery, we must first journey back to the dramatic end-of-life cycle for sun-like stars. Our own sun, in about 5 billion years, will begin its spectacular transformation. It will exhaust the hydrogen fuel in its core, causing it to swell into a red giant, expanding so dramatically that it will engulf Mercury, Venus, and almost certainly our Earth. For a period, it will shine with a fierce, bloated, orange glow, its outer layers boiling and shedding material into space. This is a phase of immense instability, where entire planetary systems are irrevocably altered. Any planets within the sun's grasp will be incinerated, their atoms dispersed into the expanding stellar envelope. Those further out, like Mars, Jupiter, and beyond, might survive, but their orbits will be dramatically reshaped by the star's mass loss. Eventually, the red giant will shed its outer layers entirely, creating a stunning planetary nebula, a colorful, ethereal shell of gas and dust. What remains at the center is the stellar core, a white dwarf. It's roughly the size of Earth, but contains the mass of our entire sun. This incredible density means its gravitational pull is immense, far stronger than any planet in our solar system. A teaspoon of white dwarf material would weigh tons. This ultra-dense core, devoid of nuclear fusion, slowly cools over billions, even trillions of years, eventually becoming a black dwarf, a theoretical frozen cinder in the far future of the universe. For astronomers, the red giant phase and the subsequent formation of a white dwarf have always represented a cosmic reset button for any interplanetary system. The intense heat, the expanding stellar envelope, and the subsequent dramatic mass loss were considered an impassable gauntlet. No planet, especially one close to the original star, could hope to emerge from this crucible intact and maintain a stable orbit near the newly formed white dwarf. The physics dictated it. Gravitational forces, tidal stresses, and the sheer violence of the star's transformation created a definitive, forbidden zone around the white dwarf, an inner sanctum where planetary bodies, if they ever existed, simply could not persist. This forbidden zone is primarily defined by two critical factors: the star's red giant expansion and the white dwarf's Roche limit. The red giant phase is self-explanatory. If a planet's orbit falls within the expanding star's atmosphere, it's gone. But even for planets that manage to avoid engulfment, the Roche limit poses a severe threat. This is the minimum distance to which a celestial body, held together only by its own gravity, can approach another more massive body without being torn apart by tidal forces. For a white dwarf, with its immense density and powerful gravity, the Roche limit is extremely close, extending much further out than you might expect. Any solid planet or asteroid venturing too near would be stretched and shredded into a ring of debris, a spectacular, albeit tragic, end to a once thriving world. However, the universe, in its infinite complexity, frequently challenges our neatly constructed models. For years, astronomers noticed something peculiar about many white dwarfs. Their atmospheres, which should be composed almost entirely of hydrogen and helium, the lightest elements, formed during the star's initial life, were frequently polluted with heavier elements. magnesium, iron, silicon, calcium, oxygen. These metals are the building blocks of rocky planets and asteroids. The presence of these elements in white dwarf atmospheres was a profound mystery. They should sink quickly due to the white dwarf's extreme gravity, so their persistent presence indicated an ongoing supply. The leading theory, supported by extensive observations, became clear. White dwarfs were actively eating the debris of planets. This metal pollution offered the first tantalizing clues that the white dwarf's forbidden zone wasn't entirely pristine. While it confirmed the destruction of planetary material, it didn't necessarily mean planets themselves were surviving. Instead, it suggested that leftover planetesimals, asteroids, or even fragments of larger planets, perturbed by surviving distant gas giants, were occasionally flung inwards, spiraling towards the white dwarf, passing inside its Roche limit and being torn apart. This created a spectacular, ongoing cosmic feast, with the white dwarf's powerful gravity ripping apart these smaller bodies, much like a cosmic blender, and accreting their metallic remnants onto its surface. This phenomenon gave us a macabre window into the afterlife of planetary systems, showing us the scraps left behind after the main course had been consumed. Yet, this still fit within the established framework. The forbidden zone for intact planets remained, a region where nothing of significant size or coherence should exist. The debris was a symptom of destruction, not survival. Then, in 2020, everything changed. Astronomers using NASA's Transiting Exoplanet Survey Satellite, TESS, and the ground-based Spitzer Space Telescope detected a transiting exoplanet system that defied all logic. WD 1856 plus 534b, this gas giant, roughly the size of Jupiter, orbits a white dwarf star designated WD 1856 plus 534. The discovery itself was remarkable, but the planet's orbit was truly mind-boggling. WD 1856 plus 534b completes an orbit around its stellar remnant in just 1.4 days. To put that into perspective, it's approximately 20 times closer to its white dwarf than Mercury is to our Sun. This means it's incredibly close, so close that it exists deep within what was previously considered the undisputed, forbidden zone for gas giants. The very existence of WD 1856 plus 534b shattered our assumptions. This planet should not be there. It should have been engulfed by its star during the red giant phase, which would have expanded to more than 100 times its current size. Even if it somehow avoided direct engulfment, the intense tidal forces during the star's transition and the subsequent migration seemed insurmountable without destroying the planet. It's a Jupiter-sized planet, not a tiny asteroid, meaning its core and atmosphere should have been obliterated by the sheer violence of its star's death throes. Yet there it was, calmly transiting its white dwarf host every 34 hours, a ghost from a past we thought impossible. The detection of WD 1856 plus 534b immediately spurred a flurry of scientific debate and theoretical reevaluation. How did it get there? How did it survive? These questions challenged the very foundations of our understanding of stellar evolution and planetary dynamics. Several theories emerged, each attempting to explain this extraordinary cosmic anomaly, this forbidden zone detected mystery. The most widely accepted explanation involves a complex ballet of gravitational interactions within a multi-planet system. Imagine a family of planets, including WD 1856 plus 534b, initially orbiting their star at safe, distant orbits, well outside the reach of the red giant phase. After the star transformed into a white dwarf, the system would still retain its overall gravitational integrity. However, the loss of a significant portion of the star's mass would have shifted the gravitational balance. In such a scenario, the stability of the remaining planets could be precarious. One leading theory posits that WD 1856 plus 534b was not alone. It likely had one or more distant planetary siblings, perhaps other gas giants or even smaller, icy worlds, that interacted gravitationally with it. This interaction could have triggered a dramatic scattering event, akin to a cosmic game of billiards. In this scenario, one of the outer planets might have been flung entirely out of the system, while its gravitational influence, in turn, kicked WD 1856 plus 534b inwards, towards the white dwarf. This gravitational slingshot mechanism is powerful enough to dramatically alter planetary orbits, sending some inwards and others outwards. The specific conditions needed for such an event are complex, requiring precise planetary masses, orbital configurations, and timing. Another possibility involves what's known as Kozyliov cycles. This is a mechanism where the gravitational influence of a distant, massive body, like another planet or even a binary star companion, can cause a planet's orbit to oscillate between being highly eccentric, elliptical, and highly inclined, tilted. During the highly eccentric phase, the planet would repeatedly swing extremely close to the white dwarf, allowing tidal forces to then circularize and shrink its orbit over time, eventually settling it into the tight, nearly circular path we observe today. This process would require significant time and the right setup, but it offers a plausible pathway for inward migration. What makes WD 1856 plus 534b even more intriguing is that it's a gas giant. While migration mechanisms can explain its inward journey, the fact that it survived intact is still remarkable. Gas giants are not solid objects. They are massive envelopes of hydrogen and helium. If it experienced extremely close encounters with the white dwarf during its migration, especially if its orbit became highly eccentric, the immense tidal forces could have stripped away significant portions of its atmosphere, or even shredded the planet entirely. The fact that it appears relatively intact suggests either a remarkably gentle migration or an unexpected resilience. The implications of WD 1856 plus 534b extend far beyond a single anomalous planet. This discovery profoundly impacts our understanding of the habitability of planetary systems. If gas giants can migrate into these forbidden zones after their stars become white dwarfs, could rocky planets do the same? White dwarfs are incredibly long-lived, far more so than main-sequence stars like our Sun. They continue to radiate residual heat for trillions of years. This extended period of stability opens up the possibility of a second-generation habitable zone around white dwarfs. While the early white dwarf phase is characterized by intense ultraviolet radiation that would sterilize any nearby world, eventually this radiation subsides. If a rocky planet, perhaps pushed inwards by a similar gravitational scattering event, could find a stable orbit at the right distance, it might exist within a region where liquid water could persist on its surface. Imagine a world, scorched and battered by its star's red giant phase, then flung into a new, incredibly tight orbit around the remaining white dwarf. After billions of years, as the white dwarf cools to a steady, gentle glow, this planet might find itself in a zone capable of supporting life. Such a world would experience eternal twilight, lit by a dim, reddish-white glow, with a sky dominated by its Earth-sized star. The energy input would be far less than from a main-sequence star, but over trillions of years, even a slow, dim energy source could potentially foster the development of life, given enough stability. Of course, there are immense challenges. These planets would be tidally locked, presenting one face eternally to the white dwarf, leading to extreme temperature differences. They would also be bathed in the remnants of the white dwarf's initial powerful X-ray and UV radiation for hundreds of millions of years, which could sterilize any emerging life. Furthermore, they would be subject to stronger stellar winds and the risk of continuous bombardment from incoming debris, as evidenced by the metal pollution problem. Yet, the possibility remains. The sheer longevity of white dwarfs offers an almost unimaginable timescale for evolution, far exceeding the lifespan of our own sun. This paradigm shift forces us to reconsider the ultimate fate of our own solar system. While Earth is almost certain to be engulfed by the sun's red giant expansion, the outer planets Jupiter, Saturn, Uranus, Neptune will likely survive. Our system, like many others, could potentially become a white dwarf system with surviving gas giants. Could future interactions between these giants, perhaps triggered by the sun's mass loss, eventually send one of them hurtling inwards, just like WD 1856 plus 534b. It's a chilling, yet fascinating, prospect for the deep future of our solar neighborhood. The discovery of WD 1856 plus 534b isn't just about one planet in an impossible orbit. It's about a fundamental reevaluation of what's possible in the universe. It tells us that our forbidden zones are often just reflections of our limited understanding. The cosmos is a realm of endless surprises, where extreme conditions can sometimes lead to unexpected outcomes. What we once considered an absolute no-go area, a sterile void of planetary destruction, has now yielded a living, breathing, planetary enigma. This single discovery has expanded the cosmic real estate, where we might eventually find life, pushing the boundaries of habitability far beyond our wildest imaginings. It serves as a potent reminder that the universe, in its elegant and often brutal physics, still holds countless secrets, waiting to be unearthed by the persistent gaze of our telescopes. As we stand at the edge of this forbidden zone, one question burns brightest. What other impossible worlds await discovery, forever expanding the cosmic tapestry we thought we knew?